So without further ado, I think it's time to call Cyprian on stage. Let's add Cyprian. Hi, Cyprian. How are you?
Hello, good morning. Very well. I'm very happy to be here. This is an amazing event, an amazing line of speakers, and I think everybody attending today will have a great experience.
Yeah, so let me just introduce you. Cyprian is the CEO of Genisoft. It's one of the most innovative Microsoft partners in Romania. He's also the chief data scientist of Soliance, which is one of the top worldwide Microsoft AI partners. Cyprian is recognized as a Microsoft Regional Director, as a Microsoft Most Valuable Professional for Artificial Intelligence and Quantum Computing. Cyprian, I can't wait to hear your talk today.
Great, thank you. Thank you very much, Ron. For today, I will tell you the story of quantum computing, which relies on one of the strangest, most fascinating fields of physics, which is quantum physics. But let me start from the beginning. It was the year 1822 when a guy named Babbage created this mechanical machine to solve polynomials. And only a few years later, around 1847, George Boole introduces a new algebra, which ended up being known as the Boolean algebra. And from that point, everything started. In several decades, we got to this, which was the first CPU. And then in even less time, we got to this, which was the first data center. And then we got to this, large data centers that are spanning the whole world. So one would think this is just an unbelievable amount of computing power. Think about tens, hundreds of data centers around the world, each one of them with trillions of gigabytes of RAM, millions and tens of millions of CPUs, and hundreds and probably billions of cores of GPU. So one would think this is just an amazing amount of computing power. And one would think, also given the fabulous evolution of this computing power, would think that, well, almost everything can be solved with this amount of power. Yet, when we think about it, the reality is that we are...
Oh yeah, your screen was blank. Sorry. Go ahead. Sorry to interrupt.
Yeah, no problem. All good with the stream?
Yeah, now it's okay. Thanks.
Okay, awesome. So yet, we're actually helpless in the face of problems that have exponential complexity, right? We all know the classical problem of the chessboard and the rice, right? Where if you start putting one tiny speck of rice and then you double with every square on the chessboard, you end up with a number that is actually too large to compute, right? 2 to the power of 64. So this is one of the challenges that we have today, and I will explain it in more detail just in a tiny bit. So examples of such problems are a lot. Think about, for example, calculating the evolution of various proteins. We are in the midst of one of the large pandemics of this century, probably, right? Should we have the capability of simulating the behavior of very complex molecules, most probably we could develop faster and better solutions for this particular problem. And then there are also problems in the realms of new materials. There are problems in the realm of, for example, optimization that we simply cannot solve with the current amount of computing power that we have. Turns out there is an amazing thing out there which is nature. In fact, nature evolves every second, every fraction of the second since the beginning of the universe, according to the laws of quantum. And in fact, it turns out that this type of evolution hides an enormous power with respect to doing different types of computations. So let me explain that in a little bit more detail. And everything at the end of the day, the big problems of humanity, they revolve around simulating the behavior of groups of atoms, whether it's about problems related to capturing carbon from the atmosphere, whether it's material science, new drugs, new materials, whether it's about simulating the evolution of systems. At the end of the day, should we be able to unlock this amazing power, it will help us advance in ways that we probably don't even imagine right now. So the problem with classical computing is that with today's power, we are severely limited in this task. And even with the amazing advancements that I've been talking about at the beginning, even if we cover the surface of the Earth with data centers, it will still mean that we can only achieve a marginal improvement in the performance of these calculations. And this is the point where classical computing literally breaks down. We will not be able, keeping this paradigm, we will not be able to solve those problems. So the big promise of quantum computing is to transform the complexity of some of these problems from an exponential one into a polynomial one, which will allow us eventually to get to the point where we can compute solutions to those problems. I think everybody remembers the famous words that were actually saying, for example, the cure for cancer will not be discovered. It will be computed. And obviously, this falls under the category of material science. New drugs are actually new materials. But think about other big problems. Think about the problem of world hunger. Turns out there is one protein in nature, we call it the pharmacoprotein, which is the fundamental building block for the process through which plants are capable of transforming light into energy. And what we've been doing for centuries, literally, we try to copy that. And our best response to that are synthetic fertilizers today. And synthetic fertilizers are not even close, remotely close to how nature's fertilizer, the pharmacoprotein, works. Should we have the capability of simulating and understanding the behavior of this molecule, we would probably be able to synthesize materials that would bring agriculture to a whole new level. It's also about carbon capture. It's also about actually leaving the Earth. One of the reasons we are still facing troubles with outer space travels, like for instance, traveling to Mars, is we still have to develop the materials capable of protecting the human body from cosmic radiation. And then it's a field that's very dear and close to my heart, machine learning. We have problems in machine learning today that we are very, very far away from solving, and that the capabilities of quantum computing are a big promise in that area. So what's actually quantum computing? The fundamental piece that lies at the core of quantum computing is the concept of a bit. And in classical computing, the bit is a little bit of a physical piece of matter that can have two states, 0 or 1. The big difference in quantum computing is that the qubit, the state of the qubit, is described by two complex numbers, alpha and beta. And the only rule that they need to obey is that the sum of the square of their norms must be 1. And this is the building block, the fundamental building block of quantum computing. So usually the first question that I always get is, hey, Cyprian, but why? Why is this the definition of the fundamental building block of quantum computing? Well, the answer is fascinating. The answer lies in what we call the postulates of quantum mechanics. The reason we call them postulates is because they are based on observation, right? Everything around the mathematical framework of quantum computing is based on these postulates, which actually translate observations of nature. This is how we observed through experiments the inner workings of nature. It's fabulous. We don't have the time today to dive into the details of this, but the short answer to the why is because this is how we see today nature working. So when we talk about the qubit, there are two fundamental states of a qubit, which we by convention name the 0 state and the 1 state, where the 0 state is where alpha is 1, beta is 0, and the 1 state is where alpha is 0 and beta is 1. And the fascinating thing about a qubit is that it can actually be in any combination of these fundamental states. So a valid state for a qubit is a linear combination of those. The simplest way to imagine that is imagine the qubit being a point on the surface of a sphere. And then the arrow indicates the point on the sphere, and then the point can move anywhere on the surface of the sphere. And some of those axes are those fundamental states, up 0, down 1. The fabulous thing about this, and again, this is how nature works, and this is one of the big problems in quantum computing, is that when you attempt to find out the state of a qubit, in other words, when you want to measure a qubit, it will always collapse to one of the fundamental states. In other words, there is actually no way to use a single measurement to find the inner state of a qubit. But I will come back to that in a moment. Now, obviously, any kind of computing system has to evolve in time. The way a quantum system evolves in time is by changing the state of qubits. And because qubits are matrices, vectors of two values, the way you change a vector with two values is you multiply it with a 2x2 matrix. Without getting into the nitty-gritty details of this, let us just say that we do find today some very important matrices like the ones that you see here. In the language of quantum computing, they are called gates or unitary operators. And if you think they sound very similar to the AND or XOR gates from classical computing, you're not far from the truth. The principle is the same. Now, one of these gates is very, very interesting. We call it the H gate or the Hadamard gate, because when you apply that gate to a qubit, you get in a state where alpha and beta are 1 divided to the square root of 2. This is called a superposition state. This is one of the fundamental properties in quantum computing. Where does the power of quantum computing actually hide? Well, not in a single qubit. The real power of quantum computing is when you start putting qubits together. So you move from a single qubit where you can have a combination of two states. When you add another qubit, you already can have a combination of 4 different states. At the third qubit, you have a combination of 8 different states. And this is where the power of quantum computing relies. If you have n qubits in your system, you can actually have a state vector with 2 at the power of n states. And 2 of the power of n, I've shown you, is a fabulous number even for small values of n. So this is why we can model very, very complex problems using the approach of quantum computing. So the power of n is the one that brings, actually the power of 2, the powers of 2 is the concept that is the fundamental explanation for the power of quantum computing. Now, let me tell you an interesting story. And for that, let's look at this particular gate or operator which works on 2 qubits. 2 qubits have 4 parameters, alpha 1, beta 1, alpha 2, beta 2. So advancing the state of a system with 2 qubits requires a 4x4 matrix. This gate is called the C0 gate or the conditional NOT gate. Leaving the mathematics of it aside, this gate describes a phenomenon that made these 2 great men become totally puzzled. And by the way, this photo of Bohr and Einstein is actually a photo during one of their discussions about the particular properties of what we call today the C0 gate. Why is the C0 gate interesting? Is because it will move 2 qubits into a state where 0, 0 has a weight of 1 divided to the square root of 2, 1, 1 has a weight of 1 divided to the square root of 2, and then 0, 1 and 1, 0 have a weight of 0, hence they are not here. Now you might wonder, well, Cyprian, why would this state be that interesting after all? Well, it is because this is called a Bell state or an EPR pair. EPR stands for Einstein-Podolsky-Rosen pair. Einstein named this one spooky action at a distance. And what it actually describes is a state that we today know as entanglement. So 2 qubits become entangled. Once they become entangled, no matter what is the physical distance separating them, their states will be correlated. So if you split the 2 qubits and put them at the opposite sides of the known universe, whenever you measure the state of one of them, the state of the other will be automatically the opposite state. This is one of the concepts that puzzles still a lot of people, and it has been experimentally proven. And by the way, it has a lot of very, very interesting applications. So let me now show you a little bit of this type of behavior in a short demo that I have prepared for today. One of the great things that Microsoft is doing is, in addition to advancing the hardware development in quantum computing, Microsoft is also significantly advancing the software side of quantum computing. QSHARP is a language designed and created by Microsoft that allows us, already using simulated environments, to build quantum programs. So I have here a simple example using a quantum simulator. And just as a side note, when you use a quantum simulator, you are severely limited in the number of qubits that you can use, again, because of the powers of 2. Simulating, say, 50 qubits on today's system, 2 at the power of 50 qubits, would be a quite difficult task. Now, what we have here is the first example. We are going to simulate the measurement of 1 qubit. So we have this measure 1 qubit piece of code where we initialize a qubit. We do it 100 times. We initialize the qubit and we measure the state of the qubit. So if we take a look into measurement QSHARP, we can see here measure 1 qubit. What it does is it creates a new qubit, an instance of a qubit, or in other words, allocates a qubit, then applies the Adamard operation to the state, which remember is equal superposition, and then it measures the qubit. So M of qubit is the measurement of the qubit. So let's quickly see how does this work. I'm gonna run my application here, and I'm expecting obviously to see the result of that. Bear with me one moment until this gets properly initialized, and it's on a different screen. So basically what I'm doing now is I'm running that particular piece of measurement on my qubits, and hopefully at some point this will come up, and you can see here. So the frequency of the 0 state is 52%. And I remember I did 100 measurements. So if I would do 1,000 measurements, this would most probably be much closer to 0.5. If I would do an infinite number of measurements, I would get eventually at 0.5, because that is the state of equal superposition. So let's see now a slightly more interesting example here. The next one that we have is we measure 2 qubits. So we initialize 2 qubits this time. Let's go here to measure 2 qubits. So we initialize 2 qubits left and right, and then we apply the Adamard operator to each of the 2 qubits. And then we measure their states. And as you might expect, there should be no correlation whatsoever between the states of those 2 qubits. So let me run this once more, and we will also run the first step where we measure the frequency. Look, this time is slightly below 0.5, but now this is what we measured with the 2 qubits. And you can see there are various combinations of 0 and 1 because the 2 qubits were set to superposition states independently. Now, here's the most interesting part. The final part of this short demo is I'm gonna take the same 2 qubits, but this time I will entangle them and then measure them. So if you look at this one here, so what we do is we apply the Adamard operator to the left qubit, and then we entangle the 2 qubits. And please notice this piece of code. We're not doing anything to the right qubit. We just set the left qubit to equal superposition, and then we entangle the 2 qubits. So let's see what will happen when we do that. And what you might already expect, obviously, is that you will see a very, very strong correlation between the 2 results. So these are the first 2 experiments that we already done. So let's run this now. So as you can see, the value of the second qubit closely matches the value of the first one. We haven't done anything to it, but we have entangled the two qubits. So welcome to the fascinating world of quantum entanglement. Now, let me come back to my deck. And the very important thing that we need to remember about these gates, and there is a good reason for that, is that together, the H, C, C0, and T gates are what we call universal gates, which means that any quantum operation can be implemented using a combination of these gates. Sounds familiar to the concept of universal classical computing? Well, it's the same principle, which means that any state in a quantum system can be reached with a reasonable margin of error by applying these states. Or in other words, a universal quantum computer is theoretically possible. That is one of the greatest results, theoretical results, that was the one that actually fueled the hope and triggered major investments in the field of quantum computing, triggered the likes of Microsoft and other large companies to start attempting to build actual quantum computers. So now that we discussed a little bit about how difficult it is to measure a qubit, and the fact that when you attempt to measure a qubit, it actually collapses, and the only way to realistically measure it, as you've seen in my demo, is to do a large number of measurements. The next big question that I always get is, well, Cyprian, but if we don't have this capability, how can we write algorithms? Imagine this simple problem. You have 3 qubits, and you have obviously 8 possible states. So what you want to do is you want to search for the result state. And everything you have at your disposal, it's something that can identify the correct result. And please, please notice the fundamental difference between finding the result and identifying the result, right? So suppose we have a way to identify the fact that the state 111 is the correct result. In other words, this is a simple framing of a search problem where we want to find the one correct state out of 8 states. One very interesting principle that we use in quantum computing is the following. What if we have a way to initialize the states with equal probabilities? And by the way, we have that. We've already seen that in my very simple demo. And then the big thing is, what if we could design an algorithm, an approach where we would change these states in a way that at the end of the process, the state corresponding to the result would become the dominant state. This is actually one of the fundamental approaches for designing quantum algorithms, and it is also known as amplitude amplification. So what we actually do, we do not measure states at every single step of the process, but we design a clever approach in which we just apply gates to the initial state in a way that at the end of the process, the result will be in a state that when measured can be identified. And believe it, there are mathematical models that support this approach. Actually, one of the first quantum algorithms that we've ever had was the search algorithm. So yes, the good news is it's possible to design and implement algorithms that overcome this fundamental universal limitation of when measuring a qubit, the state of the qubit will always collapse. So let me, at the end, say a few words about Microsoft's quest into this field. Microsoft, I believe, is doing an amazing job in advancing the field of quantum computing. And there are actually three major pillars of describing what Microsoft is doing in the field. Azure Quantum is basically an open ecosystem of partners and technologies. So we've already have behind us decades of quantum research, right? So Azure Quantum allows you to participate in this effort. The Microsoft Quantum Network is basically a community of individuals, of organizations that work together to advance a comprehensive quantum ecosystem. And then finally, the third pillar is the Quantum Development Kit, which you saw me briefly demonstrate during this talk. And the Quantum Development Kit has, in turn, three major components. QSHARP, which is a groundbreaking quantum-focused language, and you've seen a glimpse of QSHARP in action. A code optimization engine in a simulated environment that actually allows me, using my humble laptop, to simulate the behavior of a small number of qubits. And then obviously, if you're using resources in an Azure data center, you have the capability of simulating more qubits. And finally, a set of open source libraries and samples. But it's much, much more than that. Think about the fact that, excuse me, you need to develop the hardware, the physical hardware that actually implements the qubits. You need to develop a way to control that hardware, because due to the problem of the stability of qubits, your quantum hardware needs to run at what is a hairline above absolute zero. And that is in itself an amazing engineering task to achieve. On top of the quantum control, you need to interface with classical hardware. You need to build software tools and services on top of that. And obviously, the end goal is to have applications and solutions that are brought to the wider world by the partners and the developer community. So this can give you a hint to the enormous task that Microsoft is tackling in the field of quantum computing. And let me close by saying a few words about the actual building of the hardware. Microsoft is quite unique in the field of quantum computing today because they are taking the more difficult path towards building a universal quantum computer. And building a universal quantum computer, according to what we have just shown as being the definition of universal quantum computing, is a very difficult task. Microsoft is using an approach called the topological quantum computing, which actually relies on some very advanced mathematics that describe the behavior of matter. And topological quantum computing provides a level of stability for the qubits that allows actually to run computations. And imagine this, you have, say, 100 qubits. The big problem of stability is, how do you maintain the state of those qubits in a coherent situation, in a coherent state level, long enough to perform the types of computations that I've shown you? That's another fascinating problem. And Microsoft's unique approach, I believe, has the highest chance of actually providing large number of stable qubits that we can use in in some very, very powerful scenarios. So is quantum computing here to completely replace what we know about computing? Yes and no. My belief in the future of computing is we will live in a world where there's a mix of classical computing and quantum computing. Classical computing is here to stay. Quantum computing will open a whole new world of possibilities, will allow us to solve a whole new range of problems which, as you saw today, are completely out of reach for classical computing. It has been an absolute pleasure for me to be here with you today. I thank you very, very much for being here with us, and let's use the final few minutes for some Q&A. Once again, thank you very, very much.
Thank you, Cyprian, for this fascinating talk. And we got this comment from Aviad saying it was an amazing talk, and the crowd stayed through the entire session. So really, I'd like to say a big thank you. Here we have a couple of questions. So I think, first of all, one of the questions on top of my mind is at least, what do you think will be the first applied usage of quantum computing? Or, well, what will it revolutionize first?
Well, the first actual applied usage of quantum computing is something that we call quantum-inspired approaches. And it turns out that today, even if we don't have working quantum computers, some of the principles of quantum computing have inspired new approaches of classical computing algorithms, the one that we call quantum-inspired algorithms, that are already producing significant results. So it's really fascinating that we don't even have the working hardware at scale, but we're already benefiting from it. Now, when we will have the first working quantum computers at scale, any of the fields that I have enumerated will benefit. There's going to be probably not one first application of it, but multiple ones in various fields.
Okay. And another question you have, I think the audience might be interested to hear, how can they start using it? How can they experiment? What should they use? What should they learn in order to get started? Yeah,
that's a great question, Eran. So as you saw me doing the demo, the Quantum SDK, Quantum Development SDK, is an SDK that runs inside Visual Studio. So you install the Quantum SDK, it is supported by Visual Studio, and then you have two important sources. On one hand, we have a set of quantum samples, which you can download from the Microsoft's Quantum Demos GitHub repo. And the other important source is what we call the quantum katas. This is the name is inspired from martial arts. A kata is basically a series of steps that you exercise in order to get better at a certain process. So the quantum katas allow you to get acquainted with the fundamental building blocks of quantum computing and quantum programs. Those are the two very, very affordable entry-level steps that everyone can do. Even if you do not fully understand the logic behind that, you can get in touch and start exploring this fascinating world of quantum computing.
Amazing. And one final question from the audience. We're asking, what about encryption? And what is the risk that quantum computers can easily break encryptions?
Well, as we all know today, the power of any kind of encryption eventually boils down to the problem of factorization. Problem of factorization being the problem of, given a very large number, find out the two prime numbers that when multiplied give you that number. And that's basically where the power of today's cryptography relies, is in the fact that solving that factorization problem is a very compute intensive problem. So you would probably need hundreds of years of computing power equivalent to lots of data centers to break down one factorization problem. The promise of quantum computing is that it can solve even the most complex factorization problems in seconds. So you can imagine that breaking today's cryptography would be fairly easy with quantum computers. But fortunately, as we advance with quantum computing, we also advance in the field of quantum cryptography. So will cryptography 10, 15, 20 years from now be the same as it is today? Probably not. Will we have ways to keep safe levels in terms of cryptography? Probably yes, but with different approaches, most probably based on quantum approaches.
Okay, so thank you, Cyprian. I'd like to finish off with the comment by Alon, saying it was a great introduction to what's really behind the quantum label. Thanks. So I'm with Alon and with our audience, and I'd like to say a big thank you for giving us your time. And we're going to finish off by saying,
it was an absolute pleasure being here.
Thank you. And I'd like to finish off by saying that we're going to take a short break, and up next in about 12 minutes, it's 12:30 Israel time, all the morning sessions start, so you can join us then. And we're not going to be on this link on this session, so this live stream is going to close. You can go down to the link that you have it right now on the screen or on the YouTube video description. Click on it, you'll get to the Eventbrite page with all of the streaming links, and we'll be back in about 10 or 12 minutes. So thank you again, Cyprian. Thank you for all the audience, all the attendees for being with us, and have a great day. Bye, everyone.
Bye.